All right, we're back. We're on page 3 of notes 15 of Calc AB, and we're talking about what's the name of these? I don't know. Limits of Riemann sums. So close your eyes. I'm going to zoom back down there. Okay, so we're going to be talking about finding the limits of Riemann sums. We've already done some summations, and then what we're doing here is we're going to try to generalize a right Riemann sum, because it's basically all based on generalizing a right Riemann sum. So let's see if we can do that. So we're going to try to let n go to infinity. We don't just want 5 rectangles, 100 rectangles, 1,000 rectangles. We want n rectangles, and then we want n to go to infinity. As the number of rectangles increases, the amount that we're wrong decreases. So if n goes to infinity, then the amount we're wrong should go to 0. And in fact, it does. So let's see if we can generalize this thing and kind of go from there. So first, let's label some stuff. So we're trying to talk about, there's a bird just going nuts outside my window. I don't know what it's doing. Sometimes, so one of the things that I've noticed, because I've been home since March 13th, birds are nuts, and they like just get, I don't know if they get an idea in their head or they like suddenly see something or whatever. They just like flip out and they start making these weird noises, and then they'll stop and like, I don't know. Anyway, definite integral from a to b, f of x dx. So here's the graph of f of x. So this is f of x. So this is going to be a, and this is going to be b. Okay, so we did that. Sketch a few generic right rectangles. So this is always a challenge for me, because I mean, you've seen, if you've been watching some of the videos, I'm just going to like, we're going to have a couple of nice edges, and then the rest are just going to be like whatever they are. So you don't need too many. And actually, it's probably better if they're bigger. So gone. Let's say here, and then maybe like here, and then maybe like here. Okay, so these are our oh, they're not rectangles. Yeah, there, and then there, and then, well, that's bad because they're like the same height, but you know, it's the idea that counts, maybe, potentially. So if we are going to cut this up into n equal parts, then each part is going to, we're going to say delta x because we're cutting x's. These are all delta x's. And then in general, there's probably a space for this. Delta x should be the distance between these, which is b minus a, and then divided by n, the number of cuts we're going to make. So this should be b minus a divided by n. So that's the base of each rectangle. Can't stress that enough. Base of rectangle. Okay, so then we have a bunch of rectangles, and what we want to do is we're doing a right Riemann sum. So we need to know the right endpoint of each subinterval. So if I start at A, the first right endpoint is going to be at A plus delta x. And then the next right endpoint, because we always want to go back to what, in terms of A, what is it in terms of A? The next one is going to be at A plus 2 delta x. And then the next one is going to be at A plus 3 delta x. Now, the final one, if we made like one last, when you do a right Riemann sum, you always end up using that last value, right? So our last one would be like this. So like almost the same height as the previous ones. But how do we express this? Well, this should be A plus n times delta x, because we use n rectangles, right? So when we're talking about rectangle number 1, we used 1 delta x. When we're talking about rectangle number 2, we used 2 delta x's. 3, we use 3. Rectangle n, we should use n delta x's. So you can check and see if you got this right, because a plus n times b minus a over n is a plus, so you get, we get a plus b minus a, you get b. It makes sense, I mean, it has to be b, but it's nice to know that this formula that we kind of worked out here also gives us that. So let me fill in this table here. So for the first rectangle, we did a plus 1 delta x. And for the second one, we did a plus 2 delta x's. For the third, we did a plus 3 delta x's. If we're talking about the ith rectangle, it's going to be a plus I delta x's. And then if we're talking about the nth rectangle, it's a plus n delta x, which we just did the calculation. This, if we simplify it, is actually b. The last one is going to be b. So x sub I, and these are called evaluation points. This is where you find the height of the rectangle. So it's where you find the height of the rectangle. It's not the height of the rectangle. You have to plug this into the function. But this is where you find the height. These are your right endpoints. Always a plus I delta x. X sub I. I feel like when you're looking at a Riemann sum, like if you remember, if you were a little overwhelmed, and that's okay, by the last two problems that I did, where I tried to create from this a definite integral, right? So I ended up with a definite integral. The key step to that was really figuring out what x sub I is. If I could figure out what x sub I is, which I did by just kind of like looking for something that I thought looked like x sub I, then I could find the function. Once I knew the function, I could use x sub I to find the bounds, and you're good to go. So let me actually go back. That actually brings up, I think, a good point. So if I say that x sub I is a plus I delta x, and I say that delta x is b minus a over n, I think the more you write that, the better off you are. Like just keep writing them over and over, and eventually they're just like a part of you. Then x sub 0 is a plus 0 delta x. It's just a. And x sub n is a plus n times b minus a over n, which simplifies to b, right? So that's why up there before, where you may have been a little confused, I was finding x0 and I was finding xn. It's all going to come together, but we're in good shape, I think. All right, so we know, so this is where you find the height. So where x sub I is where you find the height. So the actual height is f of x sub I. So the area of each rectangle is the height, f of x sub I, times the base. So this is the height. And then this, I don't know what color I just, ooh, it's like the New York Mets. We're kind of the Knicks. Do the Mets and the Knicks have the same color scheme? I don't really know much about colors at all, but this is the base. So we're just doing base times height. All right, so I'm gonna go on to like the next page a little bit because I think it like flows naturally, but we're still supposedly on this. Okay, so if we add them all up, right? So if I add every one of them up and call it a sub n should be the sum from 1 to n of the height times the base. And this is what we did. We like approximated using this thing. And then when I was jumping the gun, I started taking the limit, right? Because I really want an infinite number. Like I want to do a of infinity, but that doesn't make sense. But I want to do a of like a trillion, a of 10 trillion, a of quadrillion, quintillion, whatever bigger things. So the actual true value, and it can be a lot of work to get to this point, but it should be the limit as n approaches infinity of the sum from 1 to n of f of x sub I delta x, where x sub I is a plus I delta x, and delta x is b minus a over n. So this gives us the information. It gives us a, it gives us b, it gives us f of x. We use n, we use a generic n for the number of rectangles that we're gonna have, and then we can set all of this up, take the limit, it'll give us the value of the definite integral. So the only thing that I think was really lacking in this description, well, no, I guess not. Maybe, I don't know. Bear with me a second here. So what we did was we made a bunch of rectangles. Each of them has a base of delta x, a height of f of x sub I. So this is delta x, f of x sub I, delta x, f of x sub I, delta x, f of, they're all delta x, f of x sub I. We add them up, that's where the summation comes from. So that's where this comes from. Adding those up gives us an approximation. Taking the limit gives us the exact value. Okay, so I'm gonna cut this here. This is a huge idea, by the way, huge. We're gonna do a bunch of them, and I feel like that's where it really starts to sink in. But after it sinks in, maybe go back and look at these pages again. So I'll cut this here, come back in the next one, and actually do something. But this is exciting. So we can figure out we can potentially figure these out as long as we can do these I formulas and all of that. So that's a different issue, but now we can set them up. So I'll see you in the next video where I think we're going to do that.